Thank you. And thanks to the organizers for having me. It's a very beautiful place to have a very nice conference. And I'd like to thank Roger and Sylvia as well. They've been wonderful advisors, mentors, and friends over many years. So one could not hope for better academic parents. Thank you. And I should, not sure if I should thank Graham or not for covering half of my talk. So, but the plan is to do things that have many similar themes to what Graham was talking about, direct sum decompositions of modules, but we'll look at it from different points of view and some different aspects of it. So all of this is things that I learned from Roger and Sylvia, or things that are based on some of their work. All right, so a setup. Oh boy. Okay, so R, everyone's used to this by now. R is going to be one-dimensional, and I want it to be Noetherian, and reduced, so there are no non-zero nilpotents. And I want the integral closure in the total quotient ring to be finitely generated as an R module. So that's going to be our setup, and I'll put an extra restriction on things a little bit later. So as Graham was mentioning, ranks of modules play a big role in studying direct sum decompositions. So we're going to take P1 through PS to be the minimal primes. Okay. And modules, I want to be finitely generated and torsion free. So classically, these are lattices over these, I guess what Hafner and Levy called ring orders, and these are maximal Cohen-Macaulay modules in this setting. Okay. And so then, so the rank of a module M then is this S tuple, R1 through RS, where the Ri is the vector space rank or dimension of the module localized at the minimal prime over the ring localized at the same minimal prime. So these are all just vector space dimensions, and then that gives us this S tuple of the module. And I want to assume throughout that R has bounded representation type. So that is, there exists some natural number with the rank of any indecomposable bounded by this S tuple n, 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 n. Okay. And equivalently, and I think this was, not sure, I think the first time this was written down was 1995 in a paper of Roger Sylvia and Roger's student Nuri, that equivalently this is that each localization of R has finite representation type, so up to isomorphism, only finitely many indecomposable modules. Okay. So that's the setting. I have a one-dimensional Noetherian reduced ring, and always has bounded representation type. After I get the setup, and set up the tools for how I'm going to look at and view direct sum decompositions, I'll first talk about the local setting, and then I'll look at a specific example of some non-local ring. So the goal is to understand direct sum decompositions. So do we have the Kroll-Riemann-Schmidt theorem? So that is, if you have two direct sums that are isomorphic, then S equals T, and after reordering, they are pairwise isomorphic. So do you have the Kroll-Riemann-Schmidt theorem? And if not, sort of how bad does it get? So this second piece is a little bit harder, and I'm not going to spend any time talking about that. I want to think a little bit more about this question. Do you always have the same number of indecomposable summands on either side? And if not, can we give some sort of measure as to how different S and T can be? Or how many different, maybe it's not just S and T, there's S1, S2, et cetera. So, okay. So as Graham did, he set up a semi-group of modules. And so then we're going to view the structure of direct sum decompositions by looking at how elements factor in these various semi-groups. Graham focused on particular modules, so you look at add of M, and then how direct sum decompositions in that work. And I want to focus more on a semi-group of all modules over these rings. So we're going to define T of R to be the set of isomorphism classes where M is an R module. And then with the operation given by the direct sum, T of R is a commutative let's see, reduced semigroup. So reduced here means that the zero module is the only unit. Okay. And as Graham noted, that if R is local, then we have direct sum cancellation. So this is actually a cancellative semigroup as well. Okay. So after we get the setup, we'll talk about local rings, and so then we're talking about factorization in a commutative cancellative reduced semigroup, but then we'll have a non-cancellative example at the end. Okay. So we have these nice observations that let us transfer information from this semigroup to the structure of direct sum decompositions. So I have that an element in T of R is irreducible just says that M is indecomposable. Right? So this is an element that cannot be written as the sum of two non-zero elements. If we have that T of R is free, okay, so isomorphic to some copy of the natural numbers, which semigroup factorization theorists call factorial. That means we have the Kroll-Remark-Schmidt property over here. And if so the factorial or the free property says if you have any element and you write it as a product of irreducibles in two different ways, then first you have the same number of irreducible elements on either side, and then second, after some permutation, the elements are the same. So half factorial, sort of a tongue-in-cheek name, I think, originally, says that really you just have the same number of summands on either side. So that's that. I'll rewrite essentially what I just erased. So if you have two direct sum decompositions in terms of indecomposable modules, then you have the same number on either side. So this is this half factorial property. And Graham shows you examples that looked like they were half factorial but not factorial. Right. Okay. So if this semigroup is not half factorial, then we need some way of measuring how far away from being half factorial it is. And so I'm going to introduce just two invariants from factorization theory. There are many more that give finer measures of non-unique factorization. And in fact, there is also invariants that will tell you, even if S equals T, how different these irreducible pieces are from these. So if S is an S semigroup, the length set of Fs, so the length of S is just the number of natural numbers, the lengths of factorization, so that S can be written as A1 plus AN, where each AI is irreducible. So in terms of T of R, it would count, you give it a module, and then the length set of that module is the number, the different numbers of indecomposables that you can use to build that module. Okay. So that's the length set. And the elasticity so one can define the elasticity of an element, which is just the supremum of this set divided by the minimum of this set. But instead, just to make life a little bit easier, let me define just the elasticity, so rho of S of the semigroup. So this is an N over M, where so the supremum of this quotient, N over M. Okay. So of course, if your semigroup is half factorial, then all of the length sets are singletons, and your elasticity of the semigroup is 1. As the elasticity gets larger, or as these length sets get bigger and more wildly behaved, then that's a measure of how far away from having unique factorization you are, and a measure of how far your semigroup of modules is telling you how far away from Kroll Remark-Schmidt you are. Okay, so there's one more piece of factorization theory that I want to introduce before we get back to some modules. Okay, so a semigroup homomorphism between two semigroups S to T is a transfer homomorphism if phi is surjective that units are mapped to units. In this case, if we have reduced semigroups, you just have one is mapped to one, and that's the only thing that's mapped to one. The important property is that if you have an element in S, the image factors in T, then you can pull back that factorization. So there exists B and C in S with phi of B is X, phi of C is Y, that's just surjectivity, and A equals BC. So these transfer homomorphisms are ridiculous, and their variations are ridiculously useful because they say these preserve length sets and elasticity. Because units are mapped to units and vice versa, and because of this, you can pull back factorizations, it means that irreducible elements are mapped to irreducible elements, and therefore you preserve length sets and all of these things. So instead of studying T of R, sometimes it's much easier to study some other object, and maybe you lose some information, but at least in terms of the lengths of direct sum decompositions, you have that still. Okay. Right. Okay. So this, now I'm going to assume that the ring R is local. So at least for a little while. So it still is, still one-dimensional, reduced, has finitely generated integral closure, and it has bounded representation type, and therefore finite representation type. Okay. And what I'm going to talk about here is probably about a decade old, but it's kind of fun, and so and it'll show you that different things can happen when we change to the non-local case. Okay. Right. So then let's see. So let me vaguely attribute this to Roger, that because there are several different pieces here. Okay, so the first, Graham mentioned this result this morning and yesterday, that this monoid of R modules sits inside T of R hat. This is the M-adic completion, and this sits inside nicely. This is divisor closed. And remember that over a complete local ring, you always have the Kroll-Remark-Schmidt theorem, and so this is in fact a free module where here I have T copies of the natural numbers, where T is the number of non-isomorphic indecomposable modules over the completion. And Roger proved, was it in 94 something, that R has finite representation type if and only if the completion does. And so just assuming that R has finite representation type gives us this. Okay. So we want to view this as the set or semigroup of extended R hat modules. So So as Graham mentioned, so a module over the completion is extended if it's the completion of a module from downstairs. Okay. And then we have another result that Graham mentioned, and I will mention a generalization of this a little bit later, but Levy and Odenthal, or this follows from their result, 1996, that so R hat extended if and only if the rank is equal whenever P and Q are minimal primes, lying over the same prime of R. So if this semigroup is sitting inside of this semigroup nicely, and if we understood what the ranks of the indecomposables are, then we can actually write down a very explicit description of this semigroup. So the last piece, in order to be able to do that, is to understand what the ranks are. So Graham this morning proved that, discussed Roger's construction that said over a particular ring, you got sort of any ranks that you wanted. But that ring is somewhat not very nice. And so if we restrict to a ring with finite representation type, then the ranks that you get are far less interesting. So this is a result from, I think, 2009. Okay. So it's classification of the ranks of indecomposable modules over such rings. This dates back to work done by many people starting in the 1960s or even earlier. Roger and Sylvia did an awful lot of this, and Sylvia's student Melissa Lucas and I kind of finished off the last little pieces. And it says if M is indecomposable, then rank of M is on the list. So it turns out that if you have one of these one-dimensional rings with finite representation type, then you have at most 3 minimal primes. So the ranks are either 1, 2, or 3, if you have a domain. And the ranks are these trivial ranks, so zeros and ones, if you have 2 minimal primes, or you can have 2, 1, a 1, 2, or a 2, 2. And if you have 3 minimal primes, then you have all of the trivial ranks. And if you a priori fix an order of the minimal primes, you can sometimes pick up this rank 2, 1, 1. So these are the only ranks that can occur as the rank of an indecomposable module over these rings with finite representation type. I have here example. So if I look at power series ring in 2 variables and x squared y minus y to the 5th probably. That should do it. Has all possible ranks. So this is one of the, it's a D6 singularity, I think. And so it has a rank of an indecomposable module of each of those possible ranks. But sometimes not all of these ranks occur for every ring. So if 3, you factor out a y and then you have an x squared minus y to the 4th. On this, yes, right. All possible. Right. If R is a Bass ring, which I'll talk more about in a little bit, so that's just every ideal 2 generated, then you have 1 indecomposable of rank, well, let me say more, and 2 minimal primes. So that we're looking at this list here, then not all possible ranks occur. So there's 1 indecomposable of rank 1, 0. There's 1 indecomposable of rank 0, 1, and all others have rank 1, 1. So the ranks that occur there aren't terribly interesting. So if I have a module over the completion, I can write down a unique direct sum decomposition in terms of indecomposables. Say there are T distinct indecomposable modules. And so then M is extended precisely when precisely when we have an equation like this where you're looking at the difference of the ranks and it has to sum to 0. Yes, thank you. Those are the ranks of the MIs corresponding to the AIs, right? So that is whether or not the module M is extended depends entirely on a set of equations, right? And how many equations are there? Well, you're going to have one equation for the difference, or the number of equations is the difference between the number of minimal primes of R and the number of minimal primes of the completion. So if you start with a domain, then you have a lot more splitting, and that's what causes interesting things to happen. So T of R is a Diophantine monoid, so where this matrix A is, let's see, Q by T, where T is the number of indecomposables, and Q is the difference in the number of minimal primes, and they're local, so the difference in the number of primes. And so that we can completely, and because we know exactly what the ranks are over these rings, then we can completely describe this A. And in fact, this was 2011. So if R has finite representation type, and this is local, then there is a transfer homomorphism say T of R to this Diophantine monoid defined by kernel of this matrix. And I'm erasing the proof, but where A is, well, something that looks like this. Let's see. And something that looks like this. Or A is just trivial. So that says in particular that either T of R is half factorial. So whenever you take any direct sum, direct sum decompositions in terms of indecomposables, you have the same number of indecomposable summands. Or the worst case is that this elasticity, so sort of the supremum of the largest length divided by the smallest length, is exactly 3/2. So 3/2 is a fairly small number. So that means that direct sum decompositions, even if not unique, can't get too bad when you have a local ring with bounded representation type. Okay. One can say a bit more about this T of R in terms of like the length sets. It turns out that they're all almost arithmetic progressions. So they're arithmetic progressions in the middle, and then there might be some noise at the end, but that gets a little far afield. Right. So now, in the remaining 8 or 9 minutes, so what happens if R is not local? Okay. And that becomes a much harder question, and so I want to restrict to Bass rings. So every ideal is 2 generated. Okay. So in that case, there's sort of, we have sort of 2 key ingredients. The first is from a paper of Roger and Larry Levy from 1985 that all about modules over Bass rings. And the second is sort of the more general Levy-Odenthal result that Graham alluded to. So piece 1, it was Levy and Wiegand. So this is our Bass ring. So I have a module. 2 modules are isomorphic if and only if their localizations are all isomorphic. So that means that they are in the same genus. And this class of M is equal to the class of N. And so here, this class of M, it's just an isomorphism class of an invertible ideal. And if you have an unfaithful module, then you have to kind of go up to a larger ring between the ring R and its integral closure. So this is an element of, they call it the Picard group of R bar, which is a disjoint union of the Picard groups of the over-rings of R. And And it behaves nicely with the direct sum, which is very convenient. Right. So it turns out that this is a disjoint union, and it's a semigroup with respect to that operation. And the second piece of information is, the second ingredient here is the Levy-Odenthal, again from 1996. And this says that, so let script M be a finite set subset of the maximal ideals. And let M be a finite module. So, and we have a family of modules, one for each M in this script M. So modules that when we localize at Q, and here Q is the union of minimal primes. Right. So then there exists some module N such that N localized at M is isomorphic to this family of X's for all M in M, and it's isomorphic, the localizations are isomorphic to M for all other M. So you can sort of pick a family of modules that at least locally are isomorphic to M, and then you can pull back to these local rings. So in particular, I guess there's one more piece maybe of information that so over a Bass ring, the singular locus is finite, and let's see, so maybe singular locus is finite, and as I observed earlier, if over a local Bass ring, you only had one indecomposable of rank 1, 0 and one of rank 0, 1, and all others had constant rank, and so in fact these are free semigroups. So putting these things together, the following theorem with Daniel Smartnig. So the map phi from the monoid of modules over R to S copies of the natural numbers. So S is the number of minimal primes still. And then we have the product of over the singular locus of T of Rm. And again, these are all free semigroups. And then to this semigroup here, and I should tell you how it's defined. So we map to the ranks. So you have an S tuple of ranks, and then you have, you localize the module, and then we have the class of R. So this is injective and induces a transfer homomorphism, preserving lengths of direct sum decomposition. to just the first piece where conveniently we can ignore the Picard group. And moreover, we can describe the image of this factorization. And so then the image, the sort of the upshot here is that phi of T of R is also a Diophantine monoid. So we can at least somewhat describe what this, the defining matrix is in terms of the rows are indexed by the maximal ideals, the columns are indexed by the minimal primes, and then the isomorphism classes over each of the localizations. And it's much more wildly behaved than in the local setting, but still the defining matrix, all of the entries are all ones, zeros, and negative ones. Nothing else happens. And so it's somewhat tame still. And so it still needs a little bit more investigating to figure out exactly what can happen. But this seems to be a good way to understand what can happen in terms of direct sum decompositions. I'll stop there. Thank you. So for certain kinds of semigroups, like a Diophantine semigroup, there are some algorithms that work in very specific cases. So.
Is there any relation between this number and the singularity of the ring?
I don't know. I haven't thought about that.
Give me an example of the Baeth ring which is not PID.
Take a, maybe, so you could do something, something like this where we have 3 points in the plane, and then if we look at the lines through the planes and look at the coordinate ring of this, maybe localized at the union of the maximal ideals. Then, so a Baeth ring, any ring of where all of the coordinate ring of an affine curve where all of the singularities are double points. Or an integral group ring where the group is finite of size that's square free. Yes.